In this video, we're going to be discussing linear equations and inequations. So let's first talk about this word equation. When I use the word equation, I'm talking about something of the format as you see here, where we have an equal sign, and we have a left side of the equal sign, a right side of the equal sign. We have different expressions on each side. So when we say equation, we're talking about something that includes an equal sign, and we have something on the left equal to something on the right. Now when we say a linear equation, we mean something that can be written in the form ax plus b equal to 0, where a and b are real numbers and a is not 0. So these real numbers, a and b, will be called the coefficients of the equation. So in practice, a lot of the times you're going to have numbers, like this could be 3x plus 2 equals 0, for example. So where 3 has replaced a and b has replaced 2. So a and b are any real numbers. And a is not 0 because if a was 0, if this was 0x plus 2, then it would no longer make sense because 2 is not equal to 0. And we want to remember when we are manipulating equations that anything we do on the left-hand side, we have to do the same operation on the right-hand side to maintain this equality. So in the example, say I have 3x plus 2 is equal to, instead of 0, let's say maybe 7. Then if I want to start manipulating this, like say I want to subtract 2 here to isolate this term 3x, I have to make sure that I do the same thing on both sides of this equals. And that's going to maintain this equality. So we have some steps here for solving these linear equations. Step 1, simplify each side. So before we start moving things to the left or to the right, we just want to make sure that each side is as simple as possible before we get started. Then the second step is to collect variable terms on one side and constant terms on the other. So that's like what I was doing above by subtracting 2. I want to keep anything with an x involved, or y, or whatever your variable is, anything with your variable on one side. Everything that's just some number, move it to the other side, and combine like terms. Then finally, isolate the variable and solve the equation. And actually the final step, and very important final step, is always check solution in the original equation. Just because you've found a solution doesn't mean that it will actually satisfy your equation. We need to go back and check. And that way we're going to make sure that we've done this correctly. Okay, so let's look at an example first. So my first step is to simplify each side. I see I have a left side, 2 times x minus 3 minus 17, and then I have an equal sign, and on the right side, 13 minus 3 times x plus 2. So we want to remove grouping symbols and combine like terms. So we can do that on each side here. On the left side, I see that I have x minus 3 in parentheses, and this 2 is multiplied in front. That means it's going to get multiplied with both x and minus 3. So 2 times x is 2x, and 2 times minus 3 is minus 6. And I don't need the parentheses anymore. Now that I've multiplied, I can just write minus 17. So that's the left-hand side. On the right-hand side, 13 is by itself, it's not involved in any grouping. So I write 13, and then I see that 3 is multiplied by x plus 2, but not only 3, negative 3 gets multiplied to x and to plus 2. So this is minus 3x minus 6. And again, I don't need the parentheses any longer. So then I want to combine like terms. What do we mean when we say like terms? Well, numbers are alike, so we can just do our usual notion of adding and subtracting numbers. Anything with the term x is alike. So on each side, I'm going to have 2x. I can combine minus 6 and minus 17. So this is minus 23. On the other side, I have positive 13 and minus 6. So I can combine those, and this is positive 7. If I do 13, subtract 6. And then minus 3x stays. So far I've simplified each side as much as I can. Now I want to do step 2. I want to collect variable terms on one side and constant terms on the other side. And I know that whatever I do on one side of my equation, I have to do to the other. So here, I think I want to add 23 because I have minus 23. Then when I add 23, these will cancel each other out. That means I also need to add 23 on the right side. So this will become 2x. And I could write plus 0, but that's not necessary because plus 0 doesn't change anything. So 2x is equal to, on the right side I have 7 plus 23 is 30 minus 3x. But I've still got a little bit of work to do because I want to get this variable term minus 3x over to the other side. So I know that I can add 3x, and that's going to cancel it from the right-hand side. That means I also need to add 3x on the left-hand side. So 2x plus 3x, these are like terms, so I can combine them. And I get 5x is equal to 30. Okay, it looks like we're getting pretty close. Our goal eventually is to have something that looks like x by itself equal to, and some number on the other side or some expression on the other side. So this last step before we get a solution and then check our solution is called isolating the variable. Since I have 5 multiplied with x, I know that if I divide by 5, I can cancel the 5's and I'll have x by itself. And I know that I have to do the same thing on the other side. So I divide 30 by 5 as well. And this gives me x equals 6. 30 divided by 5 is 6. Okay, so I found a solution. And the last thing that I have to remember to do is to check the solution back into the original equation. So the original equation was up here at the top, 2 times x minus 3 minus 17 equal to 13 minus 3 times x plus 2. I'm going to take this x equal to 6 and put it into the equation to see if it actually satisfies. So I have on the left side 2, and I'm just going to replace any place I see an x, I'm going to put 6 instead. 2 times 6 minus 3 minus 17. And that inside the parentheses, I can do 6 minus 3, so that becomes 2 times 3 minus 17. Well, 2 times 3 is 6, so this is 6 minus 17. And 6 minus 17 is negative 11. So on the left side, I got negative 11. If this is actually a solution of the equation, then on the right side, I should also get negative 11. Let's check. So I have 13 minus 3, start my parenthesis, and I'm going to, instead of writing x, I'm going to write 6 plus 2. Well, 6 plus 2 is 8, so this is 13 minus 3 times 8. And 3 times 8 is 24, so this is 13 minus 24, and that is negative 11. So I have negative 11 equal to negative 11, and that is absolutely true. So that means that x plus 6 is the solution to my equation. Okay, so that was a pretty simple linear equation. Now we have what's called a rational equation. A rational equation might look fairly similar to our linear equation, except it's probably going to involve fractions. We know from our last video that the word rational, it has this root word ratio, and a ratio is a fraction. So when we say rational equation, we're talking about something that looks like this. Our best approach when we see something that looks like this, we want to clear the denominator. So when I'm talking about a fraction that looks like, say, a over b, the number on top, or the expression on top, is called the numerator. And the number on bottom, or the expression on bottom, is called the denominator. So what do I mean when I say clear the denominator? I mean, I don't really like having these fractions here. So let me see if there's a number that I can multiply that would make this not a fraction anymore. So on the left side, it looks like if I multiply by 4, then I get to cancel this 4 with this 4 and write x minus 3. Well, that looks good, but I know that whatever I've done on the left side, I also have to do on the right side, so I need to multiply by 4 here as well, and that's going to get distributed in both places. So I have x minus 3 is equal to 4 times 5 over 14 minus 4 times x plus 5 over 7. So this is looking pretty good so far. I notice that I have a common factor here. 14 is divisible by 2 and 4 is divisible by 2. So let's go ahead and cancel that and make this 2 and make this 7. So I have x minus 3 is equal to 2 times 5 is 10, so this is 10 over 7 minus. Now here, this 4 will get distributed, so I could write this as 4x plus 20 over 7. And this is in parentheses because we remember that this minus sign actually still also has to get distributed across. So let's see if we can clear this denominator. It looks like if I multiply by 7 on this side, then it's going to distribute here and here. And in both cases, I'm going to be able to cancel this 7 with this one and this one. So I know, because I've done that on the right-hand side, I need to multiply by 7 on the left-hand side as well. So this is going to be 7 times x minus 3. And that's equal to, it would be 7 times 10 over 7. So off to the side here, I'm just going to note that 7 times 10 over 7 is just 10. So that's 10. And the same thing here, I would have 7 times this fraction over 7. It would just cancel. So minus 4x plus 20. And this is where you can see that it's important that I had these parentheses. Now it looks like we have a linear equation, just like the one we solved in the first example. So now we're ready to start following the same steps that we learned for solving linear equations. So I'm going to clear off this space to the side here so that I have some room to work, but we'll remember numerator and denominator. So my first step was to simplify each side and take care of these groupings. So I'm going to distribute this 7. This is going to become 7x minus 21. And that's going to be equal to, when I distribute this minus, I have 10. 10 doesn't change, but this now is minus 4x minus 20. I see that I have like terms on the right-hand side. So I keep 7x minus 21 on the left. On the right-hand side, I have 10 and minus 20. So that's minus 10 minus 4x. Okay, now I'm ready to move anything with an x term to one side and anything that's a constant or a number by itself to the other side. So let's add 21 to both sides. And while we're at it, let's go ahead and add 4x to both sides. We could do this in 2 steps, but I'm going to go ahead and do it in 1 step. So what do I have? Well, I have on the left side 7x plus 4x, that's 11x. Negative 21 and positive 21 cancel. So 11x is equal to, I have negative 10 and positive 21, so that becomes plus 11. Minus 4x plus 4x cancels. So this is my equation now, 11x equals 11. But I want x by itself, so I divide by 11 on both sides. And that gives me x equals 1. So x equals 1 is a potential solution to this equation, but I need to go back to the original form and check that x equals 1 is actually satisfying the equation. So on the left side, I'm going to replace x by 1. This is going to be 1 minus 3 over 4. And that's equal to minus 2 over 4, or minus 1/2. Now on the right side, I have 5 over 14 minus 1 plus 5 over 7. So that's 5 over 14 minus 6 over 7. I need to know if that's equal to negative 1/2, so I need these two fractions to be over a common denominator in order to combine them and write them as one fraction. How do I do that? Well, I can multiply by 2 on top and bottom, because if I multiply by the same thing on top and bottom, that's just like multiplying by 1, and that's allowed. So then I will have 5 over 14 minus 12 over 14. Okay, great. So I can write that as just 5 minus 12 over 14. I only need to write the bottom once if they have the same bottom. So this is just reminding you how to add and subtract fractions. And that will give me minus 7 over 14, which is minus 1/2. So these two things are equal. Very good. That means that x equals 1 is the solution to my equation. Now, if I didn't get two things that were equal, when I check at the end, if I didn't find that the sides were equal, there could be 2 reasons. Sometimes we have what's called an extraneous solution, which means that we did the algebra correctly, but we found an extra solution that isn't really a good solution. But it could also just mean that you've made a mistake. So if you got to this checking at the end and you found out that it wasn't a good solution, first thing you would want to do is recheck your work, go back through your algebra and just make sure that you didn't make any mistake. And then it is always possible that you have an extraneous solution. And that's why it's important to always check. So checking will be a part of your process. For getting full credit for working through a problem correctly, you have to do the checking. Okay, let's look at some more examples. And you'll see there's a warning here about variables in denominators. So remember that we cannot divide by 0. So we must avoid any values of the variable that make the denominator 0. So if we look at example 3 here, we have 2 times x on the bottom. We have 3 times x on the bottom as well. So right away I'm thinking, if I have x equals 0, that's probably not good. Not good for this equation, because 2 times 0 would give me division by 0. Okay. So let's just keep that in mind and start working through the problem like we did in the previous exercise. So I'm going to multiply by 2x on both sides to try to clear my denominator. So on the left side I have 5, and on the right side I have 2x times 17 over 18 minus 2x over 3x. So I see that this has also taken care of this x. I get to cancel it as long as x is not 0. And I also have a little bit of cancellation I can do here. I have a common factor, so I can make 18 9 by canceling the 2. All right, so what do I have? I have 5 equals x times 17. I'm going to write it as 17x over 9. It's common practice to write the number in front of the x, although x times 17 is the same thing as 17x, and minus 2/3. So it looks like if I multiply by 9 on this side, that will take care of the denominators. So I want to multiply by 9 on the other side. I get 45 is equal to 9 gets distributed here, and then it cancels. And 9 gets distributed here. And with this guy, I get to cross this out. I'll still have times 3. So I have 17x. I don't have the fraction on the bottom anymore. And minus 2 times 3, so minus 6. Okay, now I want to add 6 to both sides to isolate my variable term. So I have 51 is equal to 17x. Divide by 17 on both sides to get x by itself. And I have x is equal to 3, because 3 times 17 is 51. Okay, so I need to check, is x equal to 3 a good solution? Well, I didn't find x equals 0, so that's a relief. But I'm still not sure unless I plug it in. So let's look at the left side. Left side, I'm going to have 5 over 2 times 3, which is 5 over 6. On the right side, I have 17 over 18 minus 1 over 3 times 3, which is 9. So I'm going to find the common denominator multiplying by 2 on top and bottom. So I get 17 over 18 minus 2 over 18. That's 15 over 18. I have a common factor of 3 that I can cancel, so divide by 3 on top, I get 5. Divide by 3 on bottom, I get 6. So I have 5/6 equals 5/6, and that is absolutely true. 5/6 is equal to 5/6, so x equals 3 is the solution to my equation. Let's look at example 4. Again, I have a linear equation. I'm going to simplify on both sides. The left side, there's nothing I can simplify, so 4x minus 7 is fine. On the right side, I'm going to make this 4x minus 4 plus 3. So I still have 4x minus 7 on the left side. On the right side, I'm going to combine minus 4 and plus 3. This becomes 4x minus 1. So I would like to add 7 to both sides. and I get 4x is equal to 4x plus 6, and then subtract 4x from both sides. So I have 0 is equal to 6. Well, that doesn't make any sense. 0 is not equal to 6. So this equation has no solution. There are no values for x that I can plug into this equation to make this true. So if I were asked to describe the solution set of this equation has no solution. So I would say that the solution set is the empty set. And the empty set we can also write as just the curly brackets with nothing in between. So this is a situation we might encounter. All right, now let's look at example 5. In example 5, our coefficients are decimals in some cases, but we're still going to work this the exact same way. So on the left side, I don't have anything that I can combine. I have 0.07x plus 9. But on the right side, I can distribute the 0.9. So it's 0.9x plus 0.9 minus 2x. I need to combine like terms because I see that I have 0.9x and I have 2x. So on the left side, nothing changes. I still have 0.07x plus 9. And on the right side, I have 0.09x minus 2x. That's minus 1.1x and plus 0.9. So again, just because the coefficients are decimals, I don't treat them any differently. I still just do minus 2 plus 0.9 times x. Okay, and I want to get the variable terms all on one side, so let's add 1.1x to both sides and subtract 9 from both sides. So on the left side, I have 1.1x plus 0.07x. That's 1.17x. Plus 9 and minus 9 cancel. Then I have minus 1.1x and plus 1.1x, they cancel. And I have 0.9 minus 9. So that's minus 8.1. Okay, last thing I want to do, I want to divide by 1.17 on both sides because I know that I need to get x by itself. So I'll have x is equal to minus 8.1 over 1.17. Okay, and that would be fine to leave the answer in that format. If it looked like we could simplify this a little bit, and I'm sure we can simplify it some, then you're welcome to go ahead, but it should be okay to just leave it this way. Now again, we need to check whether this is a good solution. So we still have to plug it in, even though it's in the decimal form. So on the left side, we're going to have 0.07 times minus 8.1 divided by 1.17. Just replace x by the solution that we found. And then plus 9. And on the right side, we're going to plug it in. 0.9 times minus 8.1 over 1.17 plus 1 inside the parentheses. And then we'll subtract 2 times the same number. So 2 times minus 8.1 divided by 1.17. We need to check if these are the same. So we can use a calculator to help us check. So I'm checking now. And they are the same. So if I plug the left side into a calculator, plug the right side into a calculator, these do match. And so we get to say this is a perfectly good solution for our equation. If you wanted to simplify it, you absolutely may. But what you don't want to do is plug this into a calculator and say you find that this is approximately 6.92307, 692,307. So we talked about repeating decimals in our previous lecture. So you don't want to round this, because if you say this is 6.92, that's not the same as 6.92307, 6.92307, and repeating forever. So unless your problem tells you to round, which sometimes it might say round your answer to 2 decimal places, then you would. Otherwise, if you're not instructed to round, then you would rather just leave it as negative 8.1 over 1.17. Okay, so that's about linear equations. Now we want to talk a little bit about inequations. So when we say inequations, or sometimes you'll hear them called inequalities, just like an equation is something equals something, inequalities are where you have less than or greater than. So you have A is less than B, or A is greater than B, or A is less than or equal to B, A is greater than or equal to B. So when you have one of these, less than, greater than, less than or equal to, or greater than or equal to, you have an inequality. And we call it linear when we have the same setup as our linear equation. We have 2 real numbers, A and B, where A is not 0, and you have AX plus B. That's what makes it linear. Let's talk a little bit about interval notation, which is what the solutions will be when we have inequalities. When we were solving equalities, we were finding one unique solution if the solution existed. But here we're going to have an entire interval of solutions. So what is an interval? Well, in the rightmost column here where it says graph, what you're seeing is like a depiction of the real number line. So if this is your real number line, drawing here at the top of the screen, and say we have like 0 is somewhere here in the middle, you would have, if A and B are negative numbers, they'd be over here somewhere, A, B. Or if they're positive, maybe they'd be over here somewhere. Maybe this is A and B. And the interval from A to B is just going to be all of these numbers in between. And then the only question is, are we including A and including B or not? And that gives you all of these different types of intervals. So if we look at these first 4 types of intervals, if you use parentheses, that's called an open interval, and that means we're not including A we're not including b. So when we think about the set builder notation, the way we would read this is we are taking all x such that a is less than x and x is less than b. So in terms of the number line, that's all the numbers between a and b, but a is less than x, so we don't include a. That's why we use a parenthesis, because a is not less than itself. That's not true, doesn't make sense, so we don't include a here. And b is not less than b, that doesn't make sense, so we don't include b here. That's why we have parentheses. Okay, the next type of interval, as in the second line here, where you have the square bracket, that means we are including a and b. So in terms of the set builder notation, we have a less than or equal to x, and x is less than or equal to b. So now we're allowed to be equal to a, and we're allowed to be equal to b, so we include a and b in the interval. So in terms of the real number line, you use the square brackets. You could also have one of them is included and the other one is not. So in the third example here, you have x is, a is less than or equal to x, and x is strictly less than b. So when we say strictly less than b, we mean not equal to b, smaller than b. And in that case, you're going to use a square bracket for a, because a is included in your interval, and a parenthesis for b because b is not included. On the other hand, you might have a is strictly less than x, so x cannot equal a, then you have a parenthesis for a. But x is less than or equal to b, so it's okay to be equal to b, then you use a square bracket for b. Another type of interval that you might see is an interval involving infinity. So in terms of the real number line, like we drew here at the top, an interval involving infinity means that you're starting at some point, maybe you're starting at a, and you're taking everything, the entire rest of the line, and then the same question, am I including a or not? If I'm not including a, then I use a parenthesis. If I am including a, then I use a square bracket. Or going in the other direction, you might be starting at some point a and taking everything smaller than a all the way down. And the same question, am I including a? If so, square bracket. If not, parenthesis. So these are the four situations here. You have from a to infinity not including a, that's parenthesis. From a to infinity including a is square bracket. Or from negative infinity to some point b not including b is parenthesis. From negative infinity to b including b is square bracket. Or if you have from negative infinity to infinity, that's the entire line. That's everything. All real numbers is what we say. And remember from our lecture on real numbers, if the answer is all real numbers, we get to use the symbol script R. Okay, now you'll notice that any of these intervals involving infinity, you always have a parenthesis, because you can't include infinity in an interval. So infinity is always going to be open, parenthesis. But this other number, a or b, might be included, might not be included, and you have to figure that out. Okay, so here are a couple examples where we want to learn how to represent intervals in terms of the interval notation, the set builder notation, and the number line. So we have 3 rows, and we have to fill in the missing columns. So the first row, we're given the set builder notation. And the set builder notation says we want all x such that -3 is less than x is less than 10. So I know that in terms of my interval, the endpoints are going to be -3 and 10. So we write negative 3 comma 10. And then the only question is this open? Meaning, do I use a parenthesis? Or is it closed? Do I use a square bracket? Well, negative 3 is less than x. That means parenthesis. And x is less than 10. That's also parenthesis. So this is my interval notation. Now what about my number line? Well, I want to put negative 3 and 10 on the number line. Since negative 3 is the smaller number, I'm putting it to the left. The larger number goes on the right. You could draw them anywhere as long as negative 3 is on the left, 10 is on the right. And they're open, the interval's open, we already decided, so it's going to look like this. Okay? In the second row, I'm given the interval notation, negative infinity to 2, and it looks like 2 is included. Now I need to write the set builder notation. So I'm going to start my bracket, and I'm going to write x such that. So negative infinity is less than x, and x goes all the way up to 2. It includes 2, and then it stops. So the way we would write this is just x is less than or equal to 2. Any x that is less than or equal to 2 is going to satisfy this interval. And so if I wanted to graph that, I would just put 2 somewhere on my line. And I would say I'm taking, including 2, everything down forever and ever and ever. And in the third example, my set builder notation says x such that x is greater than 5. So I know that that should be starting at 5 and going to infinity. Infinity is always open, so I can go ahead and put in that parenthesis, and then I ask myself, because I have x greater than 5, should 5 be included? No, because 5 is not greater than 5. So parenthesis. And I draw the picture. That should look like I start at 5. I have open, so parenthesis. And I'm taking everything bigger than 5, so everything to the right. So when you're working with interval notation, if you're not sure, I think drawing this simple picture of the number line is actually very helpful for understanding what numbers we're actually talking about. When we say x is greater than 5, what numbers are we actually talking about? Well, we're talking about, of course, 6, 7. We're talking about 19, 30, 1,000. We're also talking about 5.1, 5.2, 5.5. So the way we depict this pictorially is we just shade in the entire line, everything to the right of 5. Oops. Put my line back. Okay. Very good. So let's just look at a couple of examples of solving inequations. We're going to follow steps that are pretty similar to what we did when we were solving the equations. There is one thing that we have to be a little careful about here. So we have to remember that when we multiply or divide both sides of an inequality by a negative number, the direction is reversed. So I'm going to put stars here, very important, and we'll see what we mean by this when we come to it. So in our first example, we have minus 9x greater than or equal to 36. Now, just like when I'm solving the equations, I want x by itself, so I'm going to divide by negative 9 on both sides. So negative 9 and negative 9 cancel, I have x. Now here's where this thing that I highlighted in red comes into play. Since we divided by a negative number, we actually have to switch instead of greater than or equal to, it becomes less than or equal to. Then 36 divided by negative 9 is negative 4. So this is x is less than or equal to negative 4. So this is the solution to the inequality rather. But we're always going to want to answer these things in interval notation. So if x is less than or equal to negative 4, what should my interval be? Well, I know that negative 5 is less than negative 4, negative 20 is less than negative 4, and negative infinity is less than negative 4. So it seems like it's going to be all of the numbers between negative infinity, and negative 4. I have a parenthesis for negative infinity. And I just have to ask myself, am I including or not including 4? I'm also going to draw my number line just to kind of help me figure it out. I'm taking, say, here's negative 4. All of the numbers smaller than negative 4, so everything on down to negative infinity. It says less than or equal to negative 4, so that means I get to include negative 4. The other way that we denote this is with open or closed dot. So I'm using square bracket here because that's what they used upstairs in the table. But let me actually, I think it will be better if we used open or closed dot. So here's negative 4. I'm going to have a closed dot because negative 4 is included all the way down to infinity. So you can draw the picture just like this. Okay, let's see part B. So part B, it looks like I have rational inequality. So I want to try to clear denominators. Now I noticed that 6 and 9 and 18 have something in common, which is that 18 divided by 6 is 3, 18 divided by 9 is 2. So it turns out if I just multiply by 18 on both sides, then I'm going to get all of my denominators taken care of in one step. So that's going to be nice. If I multiplied first by 6 on both sides, that wouldn't be a problem. But just making this observation that actually 18 is going to work, that's going to help us save a couple steps. So on the left side, I get to cross this out, and I have 3 times x minus 4. Now I multiplied, but I multiplied by a positive number. That means my inequality stays the same. And then 18 gets distributed to both places. So when I do 18 over 9, I get to cancel this 9, and I'm going to have a factor of 2 left here. 2 times x minus 2. And then here, 18 times 5 over 18, I just get to cancel the 18s. So what do I have? I have 2 times x minus 2 plus 5. So I cleared my denominators. And now I'm ready to simplify. So this is 3x minus 12 when I distribute the 3 across, greater than or equal to 2x minus 4 plus 5. And I need to combine like terms, so I have 3x minus 12 greater than or equal to 2x plus 1. I want to move my constant terms to one side, so I'm going to add 12 to both sides. And I get 3x is greater than or equal to 2x plus 13. And then I want to move 2x over, so subtract 2x from both sides. And I'm going to have 3x minus 2x is x. X is greater than or equal to 13. All right, so x is greater than or equal to 13. I want to write that as an interval. Let me draw the number line. I see that I have 13 here. I'm taking numbers that are greater than or equal to 13. Since I have greater than or equal to, I have a closed dot. And which direction do I go? I go to the right because greater than. So everything from 13 on up in interval notation, that should be 13 to infinity. And now that I've done this, I just realized that I made a mistake in part A because clearly I put a closed dot. I should have used a square bracket. So if you've been thinking for the last couple of minutes of this video that you were confused, you were right. This should have been a square bracket because we were including -4. Okay, so make sure you go back and fix that in your notes. So now we have what's called a compound inequality. That means that I have three things. I have -11 less than 2x minus 1 less than or equal to -5. And we have a note here that when solving a compound inequality, we perform operation on all three parts of the equality. Our goal is to isolate x in the middle. So what we're actually working on is the middle term here, 2x minus 1. Whatever we do to it, we have to do on both sides. So I want to add 1 here because I'm trying to get x by itself isolated. That means I add 1 here and I add 1 here. So I have -10 is less than 2x is less than or equal to -4. Okay, very good. Now again, I want x by itself, so I'm going to divide by 2. Dividing by 2 is okay because it's positive. I don't have to change the sense of inequality. So divide by 2 in all three locations. So I get -5 is less than x less than or equal to -2. I still want to use interval notation, but what interval is this? Well, let's try to draw our line and see if we can figure it out. I know that I have -5 and -2. And it looks like my x has to be bigger than 5. So I'm going to use an open circle because I'm not including 5. But it has to be less than or equal to -2. So I'm using the closed dot for -2, and it's everything in between. These will be the numbers that are greater than -5, less than or equal to -2. And in interval notation, I know I'm going to have -5 and -2. I have to decide between square brackets and parentheses. Closed dot means -2 is included. That's square bracket. Open dot means -5 is not included. That's parenthesis. Okay, and it looks like this is the conclusion of this lecture note. So we'll go ahead and end the video here.